Welcome. In this video we're going to look at how to construct the graph of a function from its definition. We'll look at piecewise defined functions, and from the graphs we'll take a look at a formal definition of what it means for a function to be increasing and decreasing. So let's start off with, what is a graph? We're looking at the graph of a function. Well, a graph is a bunch of points. And these points are in the form of ordered pairs, x comma y, where y is the output of our function, f of x. So y is equal to the output, f of x. And we can construct a set of axes. This is what we call the Cartesian plane. And we would label one axis as x and one axis as y. And we could make a table of values in order to come up with points that we would start to graph on this function. So we could label one column as x, and we could label one column as y. It would also just make as much sense to label the column x and f of x. Now we'll pick some number in the domain. So let's say x is equal to the number a. It's just a representation of some number in the domain. And we know that when we plug a into the function, we would get f of a. And that would be a point along the x-axis where x is equal to a, and where the y value of that point is equal to f of a. Let's suppose it's somewhere around here. That would give us a single point on the graph with the coordinates a comma f of a. Now suppose that we pick a second point. We've got x equals b. Let's suppose we end up with f of b being the value along the y-axis. Now this would be a separate point. Now we've got 2 points on the function. And you'd continue to do this for all of the values in the domain. Now, of course, you're never going to be able to complete all of those values on a table of values, but you'd be able to complete enough that you should hopefully gather a general shape out of it. And once you're able to gather the general shape, we can sketch the function y equals f of x, which may be some sort of curve or it might be a straight line. Now, because of the definition of a function, you have a unique output in the range for each element in the domain. So you can never have 2 points, one above another. So functions pass what we call the vertical line test. And what that line test is, a vertical line, wherever you draw it, will never intersect the graph more than once. And so you can see in this particular example, if I grab a ruler and I make this vertical, no matter where I place it, it only intersects this curve once, making it a function. Now there are examples of curves that are not functions. Take, for example, we have a circle here. Now we'll look at circles a fair bit. They have a fairly reasonable equation that defines them. X squared plus y squared equals r squared. And if we let the radius be 5, r squared would be 25. Okay, now the equation of the circle at the moment isn't the point, but the idea behind it is, if you were to look at a single point on this curve, well, you'd be able to find actually that when x is equal to 4, if you solve for y, you're going to get y equals 3. So here's a point 4, 3. And that's a point on this circle. This is the circle of radius 5. Okay, so you can see that would be 1 point on the curve. If you wanted to, you could actually put that on a table of values here, I suppose. Now, as it turns out, if you were to choose x equals 4 and you could solve, you wouldn't just get 3. You'd actually be able to get a second point on this curve, 4 comma negative 3. And so that would also be a point on this table of values. And immediately you see that for a single value x in the domain of some function, you end up with more than one y assigned to it. That makes it not a function. It doesn't pass this vertical line test. You can line up these two dots, and they should be, I've drawn this okay, I suppose. They're right above each other. So, a curve that does not pass the vertical line test is not a function. All right, now changing gear a little bit here, we have some much more interesting functions. These are called piecewise defined functions. Now, unlike a typical function where f of x is just defined as some expression of x, a piecewise defined function actually has several different rules, where f of x is defined in terms of different expressions over different intervals. So that's why it's called a piecewise function, is it has different pieces of the domain with different definitions. Okay, well, let's look at an example here. In this example, we have f of x defined in terms of 3 separate pieces. F of x equals x squared if x is greater than 1. F of x is equal to 1 minus x if x is between 0 and 1, including those numbers. And f of x is equal to just the number negative 1 if x is less than 0. Now, individually, these are like 3 separate functions, each with their own fairly common graphs, but we have to put them all together. So let's imagine separating them out initially. If we just think about x squared, we could look at y equals x squared being a fairly common graph. Hopefully you're already familiar with this. It's called the parabola, and makes this nice curved shape, sort of like a U facing upwards here. I could probably make that a little smoother. And a few points on that parabola that you can try out for yourself with the table values: 0, 0, 1, 1, 2, 4, and a few others. Now, looking at the middle piece here, we have y equals 1 minus x. And now that's a pretty common shape as well. Hopefully you recognize that as being a line. And you can rewrite that, if you like, as y equals negative x plus 1, so you can see it's got a slope of minus 1 and a y-intercept of positive 1. So we'll go through the point 0, 1 being the y-intercept, and because it's going over 1 and down 1, it's going to go through another point over here, 1, 0. So it might be good just to go and get yourself a ruler, try your best to draw a line through those 2 points, and you can see we've got a downward sloping line. Last but not least, we've got our third piece, y equals minus 1, which is deceptively easy. It means that y is always equal to negative 1, regardless of what x is. So maybe a little bit odd looking that there's no x, but that just, it doesn't mean that just means that you don't have to worry about what x actually is. Y is always equal to minus 1. So here is minus 1, and there'd be lots of points that are all minus 1 regardless of what x is. So that becomes a horizontal line. Now, to put all these pieces together, the function f of x involves little components of each of those. The graph of y equals f of x. Now, I like to think about this as almost being like you've got separate yards that the the graphs that these other functions belong in. So we've got one yard which is x greater than 1, another yard between x equals 0 and x equals 1, and then another yard between just less than x less than 0, which is to the left. So you're taking these three graphs and you're going to slice them up and place them in the corresponding yards. So as long as you already kind of know what the shapes of these graphs are, you don't have to do a lot more work. You just have to cut and paste them into the appropriate yards. So here's what I mean by that. I'm going to go ahead and make sure this is a little larger graph so we have more space to work with. And one of these yards that I'm talking about is x greater than 1. So if we want to mark off someplace on here, maybe not to scale, but this is x equals 1. To mark that off, I use a dotted line, but you got to remember this is not part of the graph. This is just there as a sort of guiding line. Okay, so what belongs in the yard greater than 1? Well, if I look back at the definition, it's the graph of y equal x squared. So I'm going to have to cut this graph a little bit here. You can see I've got the same dotted line on that graph now, and everything to the left of that line I'm going to have to trim off the graph and only include the components to the right. So starting at 1, 1, I'm working my way up to 2, 4. You can see I've trimmed off the part that completes the U shape. That part's not there. And now, to double check, you can see I've got x is greater than 1, not inclusive, so we'll use an open circle. And if you want to, you could include the point 2, 4 in here if you like. Just to give you an idea that it still goes through all of the normal points that y equal x squared goes through. Okay, jumping the fence, we're going to go 1 yard to the left, and that's between 0 and 1. And that would be our diagonal sloping line with a slope of -1. And I'm going to put that fence in right here. And another fence on the left corresponding to x equals 0, which is the y-axis. And that is chopping off everything to the left and to the right and keeping only the section in the middle. So that gives me a diagonal line from 1, 0 and 0, 1. Of course, I should probably use a ruler here. All right. Now, jumping the fence one more time, going to the left, I have another section with x less than 0, and I just need to draw the graph of y equals -1. So it's not including x equals 0, so I'll have to draw an open circle here, and then I can make that horizontal line and include all points just to the left of that open circle. And there you have it. That's what my graph looks like. The three components, x less than 0, x between 0 and 1, and x greater than 1. And that's how you can complete a piecewise defined function. Okay, now that we've taken a look at graphs a little bit more, one thing we want to look at a lot when we're talking about graphs of functions in calculus is we want to know, are those graphs increasing or decreasing? So let's just take a quick look at what we can use as a definition for increasing and decreasing. It may seem a bit obvious when you're looking at the graph, but it is nice to have a more formal definition. Now, we're going to use the same idea of interval notation, and we're going to look at a function can be increasing or decreasing on that interval. So you can imagine an interval is just some section of the real number line. It can involve round brackets or square brackets. Let's just say we've got an interval from that tick mark to that tick mark, and we're going to call this interval I, capital I, just so that we can refer to it as a name. All right, let's start with increasing. Okay, so our definition of increasing over an interval. A function is increasing on an interval, let's call it I, if f of a is less than f of b, whenever a is less than b are in I. Now, it's a bit of a convoluted definition for something that might seem pretty obvious, but it does indicate a specific direction for increase. Because of this idea here, whenever a is less than b inside the interval is one of the most important parts of this. Okay, here is our real number line, and here is our interval, capital I. Now, because a is less than b, we're free to choose a and b as we like. We just have to ensure that a is chosen always to be less than b. These can be any two numbers, but a is to the left. So now with that in mind, we're saying that f of a, which is the y value, is a smaller number than the y value when x is equal to b. So that is the direction in which we're talking about increasing. We're increasing from left to right. If you look at it the other way around, you may disagree. You might think it's decreasing from b to a, but that's not what we would consider our normal direction. We're always going from left to right. Now, what about decreasing? Now, decreasing is more or less the same definition, except for one major change here. You'll notice that we've got a change of sign. Now, only one of the signs has changed. We're still looking at more or less the same direction. We've got decreasing on an interval I if f of a is greater than f of b whenever a is less than b, our values in I. So you can see the change is only in the highlighted green inequality, but we're still talking about a less than b. So that doesn't change our direction. We're still taking a direction from left to right. Again, we've got our real number line. We've got an interval I, and you can choose a and b as you like so long as a is to the left of b. They could be really close to each other. They could be really far away from each other, so long as b is chosen to be farther away. And we're saying since it's decreasing, f of a is greater than the points to the right of a. It is decreasing. Okay, so given an example, we can describe where it's increasing and decreasing using these intervals. Instead of calling the interval I, then we can use round or square brackets to talk about the intervals where it's increasing or decreasing. Okay, here's a basic example of a function, and I've got this graphed from -2 to +2. So let's assume the domain only goes from -2 to +2. Where is this function increasing? Well, it is strictly increasing between -1 and +1. So we could write that in interval notation from -1 to +1. Now, it's hard to argue that it's increasing at x equals 1 because it's sort of the highest value it is in that interval, and there is no value to the right of that. So it's certainly increasing up to x equals 1, but we choose to use a round bracket to not include it. It also is increasing for all of the values from -1 to 0, but it's hard to argue that it's increasing at -1 because it wasn't increasing from something previous. So we choose to use a round bracket around the -1. And we've got decreasing. We see that it's decreasing from -2 to -1. Again, we'll choose to use round brackets there since it may not be strictly decreasing once it's gotten to its minimum. Now, I've tried to draw this as a straight line from 1 to 2. Something that's horizontal is not strictly increasing, nor is it strictly decreasing. So the segment from 1 to 2, we cannot say it's increasing or decreasing. It is a constant function between 1 and 2. Now, you may find that there are more than one interval of increase and decrease, in which case you can use union notation if you would like to attach more intervals together. So hopefully that gives you a first kind of look at a formal definition of something that may be easy to tell from a graph, but may be a little bit more difficult to give a mathematical description of what it actually is. We're going to be looking at increasing and decreasing using calculus, and we're not going to be needing to have a graph in front of us. So we would like to be able to express where something is increasing and decreasing just using notation. That's it for now. Thanks for watching.